Hello and welcome to Equity Education, the chemistry version, and today we're going to be looking at ionization energy. Okay, so we'll get started. So I'd like you to open up your booklets and we'll start with the definition. So ionization energy. Technically, I should really call this the first ionization energy. So first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to produce 1 mole of positive 1 gaseous ions. Bit of a mouthful. However, it's easier if we write it down as a chemical equation. So, the energy required to remove 1 mole of electrons, here's my 1 mole of electrons, from 1 mole of gaseous atoms to produce 1 mole of gaseous positive ions. Okay, and the symbol used to represent energy change is usually delta H, i.e. and our units are kilojoules per mole minus 1. Okay, so you may also ask me to define subsequent ionization energies, e.g., so we can do it for the second ionization energy. So this is the energy required to remove 1 mole of electrons from 1 mole of gaseous positive 1 ions to produce 1 mole of gaseous positive 2 ions. Pretty simple. So the only difference between our first ionization energy and our second ionization energy is that we are starting with positive 1 ions. We're going to gaseous positive 2 ions by removing again 1 mole of electrons. Okay, so why is energy required to remove an electron from an atom or an ion? Okay, have a think about it and then we'll go through it. Okay, I reckon you might have figured out these words. So the key words are: there is an electrostatic force of attraction between the positively charged nucleus and the negatively charged electrons. This requires energy to overcome. So when talking about electrostatic force of attraction, remember that's a force of attraction between something which is positive and something that is negative. Okay, another question for you. So, look at the successive ionization energies of lithium. Why do you think ionization energies increase as more electrons are removed? So here we've got some ionization energy values for lithium. So the first ionization energy is 520, the second is 7,300, and the third is 11,800. So why does it continue? Why does the ionization energy continually go up? Have a look and see if you can figure out what the missing words are, and we'll go through it in a second. Okay, so the way we would explain this is that as ionization energies increase, there are less electrons in the atom or ion. The nuclear charge, which is our amount of protons, remains the same. So we're not changing the number of protons in our atom or ion of lithium. Therefore, there is a greater force of attraction on the remaining electrons, requiring more energy to remove an electron. Which makes sense. So if we have less electrons on an atom or the ion, but we have the same positive charge, the electrons that are left are going to be held more tightly, so it's going to require more energy to remove one of those electrons. And a quick note, when I keep saying to remove an electron, that means ionization energy. Okay, right, so moving on. Factors influencing ionization energies. So it's two graphs, I want you to have a look at them. Okay, so what patterns do you notice on this graph and this graph? Okay, I'll give you a minute to think about it. Okay, so on the first graph, we can see that helium, neon, argon, krypton, xenon, and radon are all highlighted, and they're at the end of a period. So this is my first period, goes up to helium and drops all the way down to here, and then starts gradually ascending up to neon, so the ionization energy goes up, but then we go to the next period and it drops down. So you may notice that the ionization energy decreases down a group. Helium, neon, argon, krypton, xenon, radon. So it's decreasing down the group. However, in general, if we look from sodium to argon, so we're going across a period, in general, the ionization energy increases. So across a period, the ionization energy increases in general. Okay, you may notice that there are a couple of exceptions to this rule. We'll come on to that later. Okay, so what affects ionization energy? Well, there are three main factors that affect ionization energy, and the first one is the nuclear charge, which is the number of protons in a nucleus. Okay, so as we go across a period, the nuclear charge increases because one proton is added per element, e.g. sodium, magnesium, aluminium. So across our period 3, we are increasing the number of protons by 1 per element we go across. Okay, so what does that mean? That means as the nuclear charge increases, the nuclear attraction on the outer electrons is going to increase, but I'll talk about that in a bit more detail later. Okay, so number 2, another factor which affects our ionization energy is our atomic radius. So across a period, the atomic radius decreases. And the reason why is because of the increase in nuclear charge. So if we go back to our first one, we said that nuclear charge increases across the period. So because of the increase in nuclear charge, and hence the greater attraction on the outer electrons. So what do I mean by that? So I mean that as we increase the nuclear charge, the outer electrons are held more tightly, so they're held closer to the nucleus. The atomic radius across a period decreases slightly. Down a group, the atomic radius increases, which is not surprising because there is an increase in the number of shells, and that means the nuclear attraction, so this is a new word I'm using, on the outer electrons decreases. So I'll explain this word nuclear attraction in a minute. So just have a read through that and we'll go through the third one in a second. Okay, so next one. So the next factor is shielding effect. So the shielding effect is to do with the number of inner electrons. The greater the number of inner electrons or shells, we say the greater the shielding effect. The inner electrons create repulsion on the outer electrons and shield the nuclear attraction, or shield the attraction of the nucleus. This means that an increase in the shielding effect means the attraction on the is required. So this means that an increase in the shielding effect decreases the attraction on the outer electrons, requiring less energy to remove an electron. And I'll just explain this, okay, before we go on to the next bit. So shielding effect is to do with the amount of inner electrons. Okay, so if we have lots of inner electrons, this creates repulsion on the outer electrons because they're negatively charged, which means it's easier to remove an electron. Also means, and this is very simplified, that the inner electrons can shield some of the nuclear attraction, so the positive attraction from the nucleus on the outer electrons. So again, it is easier to remove an electron, an outer electron. Things which students get confused about is that if we increase the shielding effects, we will decrease the attraction on the outer electrons. Okay, so we'll carry on. So across a period, the shielding effect remains similar. Now we can explain this because we are not adding any inner electrons across a period, because we're adding onto the outer shell, which makes sense then. So the shielding effect is very similar. Down a group, the shielding effect increases due to an increase in the number of shells, which again makes sense. As we go down a group, we're going to increase the number of shells, therefore the inner electrons, so we're going to increase the shielding effect. I would have a read through of this paragraph a couple of times just to get your head around it. Okay, so these three factors, so the three factors we've talked about, contribute to the nuclear attraction. So sometimes it's called nuclear, sometimes it's just called attraction, and this means the attractive force on experienced by the outer electrons. So okay, so nuclear attraction and nuclear charge are different. Nuclear charge is our number of protons in a nucleus, atomic radius, and shielding effect all combine to talk about our nuclear attraction. And again, you might just see it described as attraction. So these three factors, remember that nuclear charge and nuclear attraction are slightly different. Our three factors are nuclear charge, atomic radius, and shielding effect. All these factors combine to perform something called nuclear attraction. And the nuclear attraction is the attractive force experienced by the outer electrons. Okay, so moving on. So there are different types of ionization energy questions. One is working out an unknown element from successive ionization energies. So, a bit of work for you. So I'd like you to draw a dot and cross diagram of sodium. Okay, so I'm sure you've managed this. We know that there are 11 electrons in sodium because the atomic number is 11. So we will have something that looks like this. So we have one outer electron on the outermost shell. So I want you to now have a look at the successive ionization energies of sodium from this graph. What do you notice? So a hint is to look back at the electronic structure of sodium. Can you see if there's any links between the graph and the structure you have drawn? Okay, and I'm sure you've realised that there is a really big jump in ionization energy between the first and the second. If we look back at our dot and cross diagram, we can see that we're removing the outer electron from the outermost shell. The second ionization energy, the electron is being removed from an inner shell. So we can describe why there's such a big jump in ionization energy, because we're moving to an inner shell which is closer to the nucleus, so experiences lots more nuclear attraction. So if we were going to write that into words, we could say this. So there is a big jump in, I'm going to write IE for ionization energy, between 1 and 2. This is because the second electron is being removed from an inner shell. This requires lots more energy. Right, so why is this important? Well, it can tell us which group an element will belong to. So this tells us, I'll put it in red, that tells us the number of outer electrons, therefore the group number. Yeah. So where you see a big jump in ionization energy, you know you're moving to an inner shell, and therefore you know the number of outer electrons and what group that element belongs to. Okay, so on to some more questions that you may be asked. So a more detailed look at ionization energy values. So we have said that the nuclear charge increases across a period. Therefore, wouldn't ionization energy always increase across a period? Well, no, there are some discrepancies. And if we go up to our graph here, we can see where some of these discrepancies are between magnesium and aluminium and phosphorus and chlorine. Okay, so we have another question to do. So I would like you to draw the box diagram of the electronic structure of beryllium and boron. Actually, I'm going to give you a bit of hints. So if you've forgotten what a box diagram looks like, I will help to draw it. So this is my energy. Whoops. Excuse me. Okay, right. Technical difficulties, you'll be back in a second. Okay, seem to have fixed it. So I'll give you a bit of a clue for this one. So draw the box diagram of the electronic structure of beryllium and boron. Beryllium's atomic number is 4. So remember, when we're drawing box diagrams, we are going to draw our orbitals, yeah? And our axes will be energy. This box represents 1s, this box represents 2s. I don't need any more box, you can do that for boron. Okay, so now we need to fill in the electrons. So we have 4 electrons. Remember, we fill the first energy level first, and then second energy level second fully. So 1s2, 2s2. I'd like you to have a go at doing boron yourself, and as well, what are the first ionization energies of beryllium and boron? I want you to find out, and what explanation can you give these for these differences? Right, so you refer to the back of the booklet. I forgot to tell you this. So your ionization energies are here. Okay, so you'll have to look it up on these this ionization energy table. Okay, so have a go at doing this and see if you can come up with an answer to fill in these missing words. Okay, so I'm sure you've been able to draw this. So these would be our box diagrams for beryllium and boron, and you'll notice that even though boron has more protons, it has a lower first ionization energy. Okay, so why is that? So we can describe this as the outermost electron in boron is in the higher energy p subshell, and there is slightly more repulsion from inner shell electrons, meaning that less energy is required to move the outermost electron. Okay, so this slightly bucks the trend across a period, and we describe it in this way. So the outermost electron in boron is in a higher energy p subshell, and there's slightly more repulsion from inner shell electrons, meaning that less energy is required to remove the outermost electron. Okay, so I would like you to now draw the electronic structure in box diagram of nitrogen and oxygen. I've been kind to you for the nitrogen. I'm not going to be kind to you for the oxygen. Do it yourself. And oops, let's make that an 8. Okay, and look up your first ionization energies in the back of your booklet as well, and then see if you can have a go at answering this question. Okay, so I'm sure you've all drawn this. So again, our first ionization energy of nitrogen is more than our first ionization energy of oxygen. Okay, even though we have added one more proton, so increase the nuclear charge. Okay, so our explanation is, so we can look at this box diagrams and it will give us some clues. So can you explain the ionization energy difference? Well, we could say there are paired electrons in the 2p subshell in oxygen. This creates repulsion, meaning less energy is required to remove the outermost electron. So here we can see that in one orbital on our 2p subshell, the electrons are paired. And it's this pairing which creates repulsion, making one of these electrons easier to remove. In nitrogen, we don't have any paired electrons. They are all in separate p subshells, which means they require more energy to remove. Okay, so these are 2 exceptions across a period that slightly bucks the trend. Okay, and we can see similar patterns can be seen throughout the periodic table. So if we go down to ionization energy, you might have to turn your head slightly. Magnesium and aluminium, yeah, same thing, and it's between group 2 and group 3, and between group 5 and group 6, phosphorus and sulfur. So we can say similar patterns can be seen throughout the periodic table. So it's always between group 2 and group 3, and group 5 and group 6. Okay, so moving on. Answering questions on ionization energies. Okay, I'm just having a few technical difficulties. We'll be back in a sec. Okay, so I just thought I'd write these for you. So these are our differences between group 2 and group 3. beryllium and boron, magnesium and aluminium, group 5 and group 6, nitrogen, oxygen and phosphorus and sulfur, and they're exactly the same explanations that we've used up here. Okay, so answering questions on ionization energies. So there are 4 types of questions that can be asked usually in an exam. So the first one is explaining the difference in ionization, energies of atoms across the period. Excuse me a second. Okay, that's why I was getting confused, because there shouldn't have been a gap, so let's try again. So explaining the difference in ionization energies of atoms across the period in general, and explaining the difference in ionization of atoms down a group, explaining the discrepancies in ionization energies across a period, and identifying an unknown element from ionization energy data. Actually, we'll change that slightly to successive ionization energy data. Let's make it slightly bigger. Okay. So in the first one, explain the difference in ionization energies of atoms or elements across the period. We're talking about in general. Yeah. So in general, the ionization energy will increase. Okay. And we've got a hint here. So always mention the 3 factors for questions 1 and 2. So we need to mention our nuclear charge, our atomic radius, and our shielding effect. Now, I've got some scrip answers, right? So it's fill in the missing blanks. If you can remember this, you should be able to answer any questions about across a period and down a group. So, how to answer this? So the first one, across a period. Explain why silicon has a higher first ionization energy than aluminium. So, silicon has a greater nuclear charge because it has 1 more proton, a decrease in atomic radius and shielding effect, and similar shielding effect. This means there is a greater nuclear attraction on the outer electrons. Therefore, more energy is required to remove an electron or the outermost electron. Right, so there are key words. So we've talked about our factors. We talked about nuclear charge, we talked about atomic radius, and we talked about shielding effect. So silicon has a greater nuclear charge, a decrease in atomic radius, and similar shielding effect. This means there is a greater nuclear attraction on the outer electrons, therefore more energy is required to remove an electron. Okay, so moving on. Our next ionization energy question is down a group. So explain why magnesium has a lower first ionization energy than beryllium. So magnesium has a bigger atomic radius as it has more shells, and therefore an increase in shielding effect. This offsets the increase in nuclear charge. This means there is let's change that, there is less, it's probably a better way to say it. So there is less nuclear attraction on the outer electrons, therefore less energy is required to remove an electron. Okay, so again we've mentioned our three factors which contribute to our nuclear attraction. So we would say that magnesium has a bigger atomic radius as it has more shells, and therefore an increase in shielding effect. This offsets the increase in nuclear charge. So offset, this word, means that it doesn't have as much effect as the other two factors. Now it's important to mention these three factors, okay? So it's an important phrase, this offset. Right, so this means there is less nuclear attraction on the outer electrons, therefore less energy is required to remove an electron. Okay, now we hadn't done any practice on these, but for question 3a and 3b, I want you to have a go at answering these yourselves. So discrepancies in ionization energy across a period, so between group 2 and group 3, and discrepancies in ionization energy across a period for groups 5 and group 6. Okay, so I'd like you to have a go at answering these two questions. Okay, so I reckon you've been able to do this if you've referred back to your booklet. So explain why magnesium has a higher first ionization energy than aluminium. So the outermost electron in aluminium is in the higher energy 2p subshell. Also, there is more shielding and repulsion from inner electrons. Therefore, less energy is needed to remove the outermost electron. Okay, and B, explain why oxygen has a lower first ionization energy than nitrogen. There are two paired electrons in the oxygen 2p subshell. This creates repulsion, therefore it requires less energy to remove the outermost electron. Okay, so next question. So another type of ionization energy question, determining an element from successive ionization energy data. So we have used the sodium as an example of this, so you should be able to answer this question as well. So I'll give you 5 minutes to answer this question, and then we'll do the next ones. Okay, the only slightly tricky bit in this is that there's two jumps, but you're looking for the biggest jump in ionization energy. So the biggest jump in ionization energy is between the 6th and 7th. So there is a big jump in ionization energy between 6 and 7, meaning a move to an inner shell. So element X must have 6 outer electrons, and we know from the question that it's in period 3, therefore it is sulfur. Okay, so last two. Describe the general trend in ionization energies from sodium to argon in terms of atomic structure, and state and explain the difference in first ionization energy between nitrogen and arsenic. Okay, so down to you. I'll give you 10 minutes to answer this. Okay, and if you used the answers to the previous question, I'm sure you've worked this out. I've changed the words very, very, very slightly just to show you how you might say it slightly differently. So describe the general trend in ionization energies from sodium to argon in terms of atomic structure. So argon has an increase in nuclear charge, a decrease in atomic radius, and similar shielding effect. Therefore, there is an increase in nuclear attraction, so it requires more energy to remove an electron. So instead of saying a greater nuclear attraction, I've said an increase in nuclear attraction. And lastly, state and explain the difference in first ionization energy between nitrogen and arsenic. Remember, we're going down a group now. So arsenic has a bigger atomic radius because it has more shells, therefore an increase in shielding effect. This offsets the increase in nuclear charge, so less energy is needed to remove an electron. Okay, so I may just change that a little bit because I have not mentioned anything about my nuclear attraction, so we need to put that in. So very quickly before the end, so we would write that there is a decrease in nuclear attraction meaning less energy is needed to remove an electron. That's a much better answer. Okay, right, so we are finished. So students seem to find ionisation energy quite difficult to get all the marks. So you must make sure you include all of your 3 factors when you're answering questions on ionisation energy, and try and use the same words in the same format that I have used as well. That will make sure that your answer is coherent and it makes sense. Okay, as usual, I hope that was helpful, and I will see you next time. Okay, bye bye.